What's going on? Got another video for you. This is business calculus, derivatives. If you're not in business calculus, but another one, watch the video. We talk about some velocity and acceleration stuff in here too. So that'll be some pretty good stuff. So we're going to learn how to find the derivatives. Basically, it's finding the derivative of a constant term and finding the derivative using the power rule. Okay, so this is the first rules that you're going to get for finding derivatives. And then the videos after this, it'll be like product and quotient rule and chain rule, that kind of stuff. So this is really important. You're fixing to learn all the techniques to find derivatives. Not in just this one video, but this video and I think the next two. So this is really important. All right, so let's get started. What do we have here? Well, we've got techniques of differentiation. So the derivative, this first thing right here, is just telling us that if we're taking the derivative of a number, of a constant, then that's just zero. And then this derivative here, this is the power rule. If you have x raised to a power, then all this is saying is you take the exponent, bring it down in front, and subtract 1 to find the derivative. All right, so let's look at some examples. So here we've got y prime. Whoop, let me change colors. We've got y prime is equal to, now here we're taking the derivative of a number, so that's just 0. Yeah, it's that easy. All right, let's look at the number 2. So we've got y prime is equal to, now notice this one we have x to the n, x raised to a power. So what do we do when we have x raised to a power? Well, that exponent comes down in front and then subtract 1. So the 3 comes down in front and then subtract 1 from the exponent. So 3 minus 1 is 2. And there's your answer. It's a lot easier than what we did in the last video when we were doing the limit as h goes to 0. It's a lot easier than that. All right, so let's look at this one. We don't have anything up here that tells us how to find the derivative of a square root. The only thing we know how to find the derivative of is x raised to a power. Well, couldn't we do this? Couldn't we say y is equal to x raised to the 1/2 power? That's the same thing, right? If you go from radical form to exponential form, you remember that? So now we can say that y prime is equal to 1/2, so the 1/2 comes down, times x, and then what do? We subtract 1 from the exponent. So 1/2 minus 1 is negative 1/2. And then we can make this exponent positive. So y prime is equal to 1 over. So do you remember this x to the negative 1/2? That's like x to the negative 1/2 over 1. So we can actually move that to the denominator. And what happens when you move it to the denominator? It changes the sign of the exponent. So that's 2x to the 1/2. And so we could write this as 1 over 2 square root of x. And this would be your answer right here. Now, do you need to change this to a square root? You can. I guess it's really just going to depend on what your teacher wants you to do. They may let you leave it like this. They may let you leave it like this, or they may want you to write it as a square root. It doesn't really matter to me. Actually, I would, if you're in my class, I'd probably want you to just go ahead and write it like this, like I did here. Okay. So another example I want to work that I didn't write down, but let's do another one. What about if we do y equals the cube root of x squared? What if we wanted to find the derivative of that? Okay, so let's remember from algebra, if we have a to the m and we're taking the nth root of that, do you remember that you can rewrite this as a to the m over n? Okay. So that's going from radical form to exponential form. So how would we go about writing this? Well, we would have to change it to y equals x to the 2/3. And then we can take the derivative. So y prime is 2/3 x. The exponent comes down. Subtract 1 from the exponent. So we have, what is that? That's 2/3 minus 1 is what? Negative 1/3. So that's negative 1/3, which is 2 over 3x to the 1/3. And you could leave it like that, or you could go on and write it as 2 over 3 times the cube root of x. Okay, and there's your answer. So, you could leave it like this, or, I wouldn't mind so much if you left it like that in my class. And I guess the same thing over here, you could leave it like that if you wanted to. Go ahead and make those, you can make those exponents positive. That would be fine. All right. So basically what we're doing is we've had two problems here where we didn't have, or they didn't give us x raised to a power. They wrote it as radicals. And what did we do? We changed it to where it was x raised to a power, and then that allowed us to use this power rule here to find the derivative. Okay, so what about this one? Y equals 1 over x squared. Do we have x raised to a power? We do. We have x squared, but the problem with that is it's in the denominator. We don't know how to take the derivative of that if it's in the denominator. So what we need to do is we need to move that term up to the numerator. So if you remember, when you move something across the fraction bar, it changes the sign of the exponent. So that would give us x to the negative 2. And so now y prime would be negative 2. The exponent comes down. Subtract 1 from the exponent. So negative 2 minus 1 is negative 3. And then this would give us negative 2 over. And remember, that's over 1, so we're going to move it down to the denominator to make the exponent positive. So we would get negative 2 over x cubed. And then this one right here, well, that's easy. The 7 comes down. Subtract 1 from the exponent. So that would be 7x to the 6th. And then what about this one? Well, y prime is what? Well, the 4 comes down. 4 times 3 is 12. Subtract 1 from the exponent. 4 minus 1 is 3. And there's your answer. And you can also have multiple terms. Well, to take the derivative of this, we just take the derivative of each term individually. So we would have f prime of x is equal to, so the negative 2 comes down. Subtract 1 from the exponent. Negative 2 minus 1 is negative 3. And then the derivative of 7, well, 7 is a constant. So the derivative of 7 is just 0. And so now we would get f prime of x is equal to negative 2 over x cubed. All right. So you can see it's not too bad so far. All right, what about this one? Here we have several terms, don't we? So we've got f prime of x is equal to, so take the derivative of each term individually. So the 3 comes down. 3 times 5 is 15. Subtract 1 from the exponent. So that's the derivative of 5x cubed minus, and then we take the derivative of the next term. 2 times 4 is 8. Subtract 1 from the exponent. 2 minus 1 is 1, so that's x to the first, plus the derivative of 12x. Okay, I'm going to go ahead and just write this down, and then I'm going to go off to the side and show you step by step this derivative of 12x. So the derivative of 12x is just 12. And then the derivative of the minus 8, that's 0. And so this would be your derivative here. So let's look at this. Let's look at this y equals let's say we have y equals 12x, and we want to take the derivative of that. Well, this is a power of 1, right? Now, keep in mind, when you're taking the derivative of 12x, you don't have to show all this work. At least if you're in my class, you don't. You don't have to show all this, what I'm fixing to show you. So the 1 comes down. So 1 times 12 is 12. Subtract 1 from the exponent. So 1 minus 1 is 0. And so y prime is 12 times. Now, what is x raised to the 0? Well, remember, anything raised to the 0 power is 1. And so we get y prime is 12. And that's how I got this 12 right here. I just wanted you to see that. But you don't have to do that. Just remember, if you have a number times x and you're taking the derivative of that, and it's just a number times x, well, then the derivative is just the coefficient of x, that number in front of x. Okay? All right, so that's finding the derivative, okay, using the power rule. And then we know how to find the derivative of a constant. And like I said, in the next couple of videos, we're going to learn product quotient rule, chain rule. All right. So let's look at this example here. Well, there we go. All right. So it is estimated that X months from now, the population of a certain community will be P of x equals x squared plus 20x plus 8,000. Okay? At what rate will the population be changing with respect to time 15 months from now? All right. So what do? Well, we learned in the last video that the derivative is a rate of change. So to find that rate of change, or to find how it's changing, we need to take the derivative of this thing and then evaluate it at 15. And so let's do part A. We have P of x is equal to x squared plus 20x plus 8,000. And if we take the derivative of that, so P prime of x, so just the derivative of each term, that's 2x plus 20, and then the derivative of 8,000 is just 0. Okay? All right. So now, if we do P prime of 15, that is equal to 2 times 15 plus 20, which is 30 plus 20, which equals 50 people per month. That's the rate of change after 15 months. Okay? All right, so that's not too bad. All right, so part B, it says, by how much will the population actually change during the 16th month? So actually change. So the change, the actual change, the change in population would be P of 16 minus P of 15. So we would take the actual population in the 16th month minus the actual population in the 15th month. And so that would equal, so P of 16, now notice what it's saying. It's saying P of 16 minus P of 15, not P prime. So we've got to take the 16 and plug it into the original. So that's going to be 16 squared plus 20 times 16 plus 8,000 minus, and then then we plug the 15 in, 15 squared plus 20 times 15 plus 8,000. Now, be careful here. Remember, it's P of 16 minus P of 15. So this right here where you plugged in 15, you've got to put all of that in parentheses. And we get 51 people. So that would be the actual change. All right. All right, so I hope all that made sense. And yes, from here on out, it's word problems. Okay, and it's word problems based on where we have to take the derivative. Okay. All right, so let's look at this relative change. Relative change is the change in Q divided by the size of Q. Okay, and Q is a quantity. So it's the change in quantity divided by the size of the quantity. And here's an example. It's nothing we're going to work out, but it's going to give you an idea, something about of the things you can tell from this, the change in Q divided by the size of Q. So it says a yearly rate of change of 500 individuals. Okay, so we've got a yearly rate of change. There's a change of 500 people in a city. And the total population is 5 million. Okay? So if we look at the relative change, that's 500 divided by 5 million, which is 0.0001 or 0.01%. Okay? So, you're saying, okay, the yearly rate of change, if it changed, let's say we lose 500 people in a city. Not really a big deal. I mean, we got 5 million, so it's really not that big of a deal. And you can see it's 0.01% of the 5 million people. But look at this. If we lose 500 people in a city, okay, of a town that has 2,000 people, so this town only has 2,000 people, well, that's 500 divided by 2,000 is 0.25. So that's losing 25% of the people. That's a big deal. So you might, you look at somebody and you tell them, well, you know what, we lost 500 people in the city. Well, it really doesn't tell them anything, but it would tell them more if you said, yeah, last year we lost 0.01% of the people in our city. And you say, oh, well, that's not that much. But if you said we lost 25% of the people, and said, whoa, that's a lot. And so you see the difference? All right. So we have relative and percentage rates of change. So the relative rate of change of a quantity Q of X with respect to X is given by the ratio Q prime of X over Q of X. Okay, that's your relative rate of change. That's what we just talked about that up here. All right, so you do the derivative of Q divided by Q. All right, and that's what this means up here. It's the change in Q. Isn't that what the derivative is? It's the rate of change. Okay, and then this Q of X would be the quantity. For instance, how many people there are. And then the corresponding rate of change, the corresponding percentage rate of change of Q of X with respect to X is Q prime of X over Q of X times 100. And look, that's all we did here. See, we found the relative rate of change here. We got the 0.25. The change was the 500 individuals, and the total quantity was 2,000. So that gave us the 0.25, which is our relative rate of change. And then if you take the 0.25 times 100, that's where that gives you the 25%. So that's what this is. We're multiplying by 100 to get the percentage. All right. So let's look at this word problem here. It says the gross domestic product, GDP, of a certain country was this. They give you N of T is equal to T squared plus 5T plus $106 billion. This is in billions of dollars. T years after 1995. At what rate was the GDP changing with respect to time in 2003? All right. So they want to know for part A, at what rate was it changing? All right, so for part A, well, the rate of change, well, we would take the N of T, right? That's t squared plus 5t plus 106, and we would take the derivative of that. So that's n prime of t is equal to 2t plus 5, okay? Now, what do they want to know? They want to know at what rate was the GDP changing with respect to time in 2003. So we would evaluate this n prime of t, we would evaluate it at what? At 8. Well, why 8? Well, because it tells us the GDP of a certain country was this $1 billion t years after 1995. So 1995, this represents a time of t equals 0. And then 2003 would be 8 years later. Okay? And so this would give us 2 times 8 plus 5, which is equal to 21 billion, right? $1 billion per year. And you're thinking, hey, you know, that's a lot of money. Well, it is. It is a lot of money. But let's look at part B. At what percentage rate was the GDP changing with respect to time in 2003? So what percentage of it? What's the percentage of it? Well, remember, that would be n prime of 8 over n of 8, right? Remember, the percentage is the derivative over the function. And we do need to multiply it by 100. Okay? All right, so we do have to multiply it by 100. I had to pause the video and plug my laptop up, my tablet up. All right, and so we would need to add multiplying this times 100. And so that's going to be 100 times 2 times 8 plus 5. Whoop. I know I already calculated that to be 21, but I'm going to show you that we're taking the 8, plugging it into the derivative, and then that would be divided by 8 squared plus 5 times 8 plus 106. And that is equal to 100 times 21 over 210, which would be 10% per year. Okay, so it would be 10% of the money per year. All right, so that's not too bad. That's not bad at all. All right, so now let's get to this right here. It says rectilinear motion. It says if the position at time t of an object moving along a straight line is given by s of t. Okay, so that's the position of the object given by a function s of t. Then the object has velocity v of t is the derivative of the position, the s of t. Acceleration is the derivative of the velocity. Okay, velocity is change in position. Acceleration is the change in velocity. And keep this right here in mind, that an object is advancing when the velocity is positive, it's retreating when the velocity is negative, and it's stationary when the velocity is 0. And then an object is accelerating when the acceleration is positive and decelerating when the acceleration is negative. So, just to kind of give you a picture, if you look at this, if you have an object traveling like this, okay, here it is advancing, here it is stationary, here it is stationary, here it is retreating. See here, it's moving in a positive direction, then it's stationary, it starts retreating, and then it's stationary, and then it starts advancing again. That's what it's telling you. And we'll draw a little picture on this with this next word problem that we have. Okay, but there's just to give you an idea of this right here. Okay. All right, so it says the position at time t of an object moving along a line is given by s of t is t cubed minus 6t squared plus 9t plus 5. Find the velocity of the object and discuss its motion between times t equals 0 and t equal 4. All right, so part A, we've got s of t is equal to, I'm just writing down the function again, t cubed minus 6t squared plus 9t plus 5. And its velocity, v of t, is equal to 3t squared minus 12t plus 9. That's the velocity. Okay? So when it asks us to find the velocity of the object, that's this. That's its velocity function. Okay? Then it wants us to discuss its motion between the times t equals 0 and t equal 4. So in order to do that, we're going to need to take the velocity function, set it equal to 0. So I can factor out a 3. And that's going to give me 3t minus 3, t minus 1 equals 0. So t equals 3 or t equals 1. Okay? So what I did here is I set the velocity function equal to 0 and solved. So I found out at what time the object's velocity is 0. In other words, when it's stationary. Okay, you see that? It's stationary because, see, the velocity is 0 when t equal 3 and t equal 1. And if I look at that on a number line, see how it breaks this up? And we're discussing from t equals 0 to t equals 4. That's what we want to know. We want to discuss its motion between times t equals 0 and t equals 4. So you can see here, I've got 1, 2, 3 regions I'm looking at. Well, if I look at this region right here, let's look at this region and say we pick t equals 1/2. Here let's pick t equals 2, and here let's pick t equals 3.5. Okay? And if I take the 1/2, and I plug it back into the velocity function, okay? Now, before I do that, do you agree with me that this function here is the same as this one? I'm sorry. It's the same as this one. It's the same thing. It's just this is factored, okay? This is the factored version of this. So if I take the 1/2 and plug it into here, what's 1/2 minus 3? I don't really care about the exact answer, but do you understand that 1/2 minus 3 is negative, and 1/2 minus 1 is negative? You see that? And then we've got the 3 out here. This 3 out here is positive. So a positive times a negative is a positive. So that means that's positive in here. And then if I plug the 2 in, well, the 3 is positive. 2 minus 3 is negative. 2 minus 1 is positive. So this would actually give me a negative answer. This is negative in here. And then when t is 3.5, well, the 3 here is positive. 3.5 minus 3 is positive, and 3.5 minus 1 is positive. So this would give me a positive answer. And so you might be thinking, okay, that's good and everything, but what is this showing us? Well, it's showing us that it's advancing here, retreating here, and advancing here. So we can see that from when t is between 0 and 1, it advances from what? From s of 0, which is equal to what? Well, what's s of 0? If I take the 0 and plug it back into this original function, I get 5. 2, so it's advancing from 0 to 1 to s of 1. And what's s of 1? Well, I plugged the 1 in for t here. And then you can do that in your calculator, and you're going to get 9 as an answer. Okay? And then when t is between 1 and 3, it what? It retreats from s of 1, right? From s of 1 to s of 3. Well, what's s of 1? S of 1 is 9. 2, s of 3. Well, what's 3? We'll plug 3 in to this one right here. Okay? And when you do that, you get 5 as an answer. And then when t is between 3 and 4, say the 3 and 4 here, it advances. So it advances from s of 3, right? From s of 3, which is 5, to s of 4. And what's s of 4? Well, if I plug 4 into t here, I'm going to get 9 as an answer. And so what that would look like, if I looked at that, so we would have, say, 0 here, this would be 5, and this would be 9. Okay? And so we're starting here, and as I'm going from s of 0 to s of 1, that's going here, right? That's going here. And then, so this right here, this point right here, would be s of 1. And then from s of 1, it starts retreating back to here. And this would be what? This would be s of 3. See, it's retreating from s of 1 to s of 3. It's going from, see, 9 to 5. And so then once it gets here from s of 3 to s of 4, see, this would be my s of 4. It's going from 5 to 9. See, from s of 3 to s of 4, it's going from 5 to 9. And so that's what this would look like. Okay? All right, now let's look at part B. What does part B say? It says, find the total distance traveled by the object between times t equals 0 and t equals 4. Okay, so the total distance. Okay, so the distance, okay, all right, so from s of 0 to s of 1, all right, so that's going from here, from here to here. So that's going to be 9 minus 5 plus, and then s of 1 to s of 3. So that's going to give me my 5 minus 9, and then from s of 3 to s of 4, that's going to be 9 minus 3 plus 9 minus 3. That's the distances. See, I'm going from here to here, so that's my 9 minus 5. But then I'm going from here to here, so that's going to be 5 minus 9, and then I'm going from here to here, that's going to be the 9 minus 5. Now remember, we're talking about the distance traveled, so we are going to have to take the absolute value of each of these, and this should be a 5 right here. And so that's going to be absolute value of 3 plus absolute value of negative, not 3. How about 4? Does 4 sound better? negative 4 plus absolute value of 4, which is 4 plus 4 plus 4, which is equal to 12. Okay, so that's the total distance that it traveled. All right, and then we've got part C. What does it say? It's kind of jumbled up. It says, find the acceleration of the object and determine when the object is accelerating and decelerating between times t equals 0 and t equals 4. So let's find the acceleration of the object. So remember, the acceleration is what? It's the derivative of the velocity. So let's see. Here's our acceleration function, 3t squared minus 12t plus 9. 3t squared minus 12t plus 9. And so the acceleration is equal to 6t minus 12. There's your acceleration. That's what it's asking for. And then it wants to know, when is it accelerating and when is it decelerating? So what we're going to do is take the 6t minus 12 and set it equal to 0. And so that's going to be 6t equals 12t equals 0. So that would be when the acceleration is 0, when t equals 2. So I'm going to do the same thing. I've got t equals 1, t equals 3. All right. And then, of course, you know, over here, we're concerned with t equals 0 to t equals 4. That's what we're looking for. So we got these two regions right here. So if I take the t and plug it into my acceleration, look at this. A of 1, I'm taking this 1 here, plugging it in, that's going to give me 6 times 1 minus 12, which we can see that's negative, right? That's negative there. I don't care. I know it's negative 6, but I don't care that it's negative 6. I just care that it's negative. And then A of 3 is equal to 6 times 3 minus 12, which we know that's positive. 18 minus 12 is positive. So we can see that this thing is accelerating when t is between 2 and 4, and it's decelerating when t is between 0 and 2. And that's what they wanted to know there. All right. All right, so this is the last thing right here. Okay, let's look at this. It says, suppose an object is projected vertically in such a way, and we say that the an object is projected vertically. That means projected means thrown, fired, or dropped, something like that. Okay, projected vertically in such a way that the only acceleration acting on the object is the constant downward acceleration g due to gravity. Now, do we know what the acceleration due to gravity is? Well, if you're in feet and seconds, g would be 32 feet per second squared. And if you're in meters in seconds, the acceleration due to gravity would be 9.8 meters per second squared. Okay, so depending on if you're in feet or meters, that's going to depend on if you're using 32 or 9.8 for g. The height h of t is negative 1/2 times g times t squared plus v naught times t plus h naught, where v naught, this v naught here, is your initial velocity, h naught is your initial height. So the initial height, that's what height are you at when you drop or throw the object in the air. And then your initial velocity is with what velocity are you throwing. All right, so let's look at this. Suppose a person standing at the top of a building 112 feet high throws a ball vertically upward with an initial velocity of 96 feet per second. Find the ball's height and velocity at time t. Okay, so for part A, the ball's height. So let's just go ahead and write down. Let's write our formula down. -1/2 g t squared plus v naught t plus h naught. Now you can see in our problem that g is equal to 32, right? Because we're in feet and seconds. We're in feet. The initial height is 112, so h naught is 112. And then v naught, the initial velocity, is 96 feet per second. That equals 96. So our h of t is equal to -1/2 times 32 times t squared plus 96 times t plus 112. So h of t is equal to -16 t squared plus 96t plus 112. That is your height. Okay, that's what we found when it asked us for the ball's height. Now they want to know the ball's velocity. Okay, well, the velocity, v of t, remember, that's the derivative of h of t. So that's -32t. Oop, I forgot my t here on the 96. So that's -32t plus 96. Okay, and remember, okay, so that's your velocity. And remember, this is in feet. And this velocity, that would be in feet per second. Okay, so that's the answer to part A. Now let's look at part B. What does it say? It says, when does the ball hit the ground and what is its impact velocity? All right, so we want to know when does it hit the ground, at what time, and we want to know what's the velocity of that object when it hits the ground. So when does it hit the ground? Well, that would be when the height is 0, right? So that would be -16t squared plus 96t plus 112, and we want to know when does that function equal 0. So now we've got to factor this thing, don't we? I don't even know. Does 112 to 16? Yeah, 16 goes into 112 evenly, and 16 goes into 96 evenly. So what I can do here is I can divide both sides, everything, by -16. Make it easier for us to factor. And I'm dividing by a negative to get rid of the negative in front of the squared. So that's t squared minus 6t minus 7 equals 0. And so now we can factor this thing. So that's going to be t minus 7 times t plus 1 equals 0. So t equals 7 or t equals -1. And we know that that's not going to be the answer. So at t equals 7, so we can say object hits the ground at 7 seconds. Okay. We know it's not -1. You're not going to have a negative time. Okay. And then it wants to know what's the impact of it. What's the velocity at impact? Well, when does it hit the ground? It hits the ground at 7 seconds, and so we just evaluate the velocity function at 7. And remember, here's your velocity function. So that's -32 times 7 plus 96. And punching all that into your calculator, you're going to get negative 128 feet per second. And that would make sense. The negative 128, that means that's velocity. That means it's going downward, right? It would be like it's retreating, okay? Because you threw the ball up, it's going up, and then it's coming back down. All right, so let's look at part C. When is the velocity 0? What is the significance of this time? So when is the velocity 0? Well, let's write the velocity function down. V of t, what is that velocity function? That's negative 32t plus 96. That's your velocity. So they want to know, when is the velocity 0? Or when is that object stationary, right? That would be the same thing. So all we do is we take the velocity function and set it equal to 0. And so we get negative 32t equals negative 96. So t is equal to 96 divided by 32 is 3. So at 3 seconds, that's when it's stationary. That's when the velocity is 0. And so they want to know what significance does this have? Well, if we look at this, if you take the 3 here, and then you take a value over here, t equals 2, and you take a value here, t equals 4. So if we plug the 2 in to our velocity function, we get a positive number. If we plug the 4 in, we get a negative number. So we can see that the velocity is positive. So the ball is rising when t is less than 0. And then when t is greater than 0, the velocity is negative, so that would tell us that the ball is falling. So you can see, if you're up here at the top of a building and you throw the ball upward, it's going to go up and come back down. So the ball is traveling upward, okay, from time t equals 0. That's when you throw it at time t equals 0. It's traveling upward, and it reaches this height here after 3 seconds, and then it starts falling back to the ground. And that's so from t equals 0 to t equal 3, the ball is rising here, and then from t equal 3 to t equal what? T equal 7. Oh, where did I get 7 from? Well, 7 is when t equals 7, that's when it hits the ground. So from the time t equals 3 to t equals 7 seconds, the ball's falling. And that's what that's telling us there. And then we've got part D. Let's see, where's part D? How far does the ball travel during its flight? So how far is the ball traveling? Okay, so we've got total distance traveled. So what is that? Okay, so it's traveling up. So if you look at this, so the ball starts at h of 0. And let's go ahead and write our position function. That's negative 16t squared plus 96t plus 112. So at h of 0, if I plug the 0 in for t, I'm going to get 112. And then at h of 3, okay, that's going to give me the maximum height, right? That gives me my maximum height at h of 3. So if I plug 3 in for t into my height function, I get 256 as an answer. Okay, so think about this. So the distance it traveled from here to here, this height here is 112, this height here is 256. So the distance from here to here would be 256 minus 112. So that's this distance right here. And then plus 256. So it reaches this height here, and then it falls from here down to 0, to a height of 0. So from here to here is 256. So that would be plus that 256 there, which is equal to 400 feet. All right. And that's your answer there. So hopefully all of this made sense. It's just crystal clear now. So you learned a lot today, and see how fun this stuff can be. So I hope this video helped. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.